Okay. Good afternoon, everybody. I hope each one of you are fine, taking care of yourself physically and mentally. So the seminar of this afternoon will be given by Dr. Tim Lichtenberg. Dr. Lichtenberg has a bachelor degree of science in physics from the University of Göttingen in Germany. He has a master degree of science in physics from the same institution, and he's a doctor of science in planetary physics, star and planet formation from ETH Zurich in Switzerland. Currently, he is a postdoctoral fellow at the University of Oxford in the United Kingdom. He's mainly working in formation of early and early evolution of terrestrial planets. Today, Dr. Lichtenberg will talk about geophysical evolution during rock planet formation. I just would like to remind all of you that if you have any question or comment, please write in the chat. And at the end of the presentation, I will call you to say it directly. So, Tim, you may start your presentation, please.
Okay, thank you so much. Let me try that. Okay. So I hope you are seeing my presentation now.
Yes, yes.
Okay. All right, great. Do you also see my mouse?
Not really.
Okay, well,
No.
then I'll describe it. Okay.
Okay.
Thank you so much. Again, hello everyone. Thank you so much for giving me the chance to present my work and that of my collaborators to you. Yeah, as was said already, like I'm currently a postdoc at the atmospheric physics at Oxford, and I'm sponsored by the Science Foundation, especially the collaboration The Origins of Life. So my interest is how a rocky planet formation basically translates into creating habitable or uninhabitable worlds, either in the solar system or in exoplanetary systems. So, and my talk today will be kind of a little bit of a wild ride. I'll start from the exoplanet scale, motivate my work in that direction with the diversity that we observe in the rocky exoplanets and the exoplanet census in general, and then I will come back to the solar system and I will argue basically that our understanding of planet formation in the solar system, seeming small details, translate to quite different predictions that we make for the exoplanet census, or that basically have severe implications for how we interpret what we find among extrasolar systems. And then I will come back and I'll try to make I'll try to make some predictions and draw some conclusions from our previous work that may help us to decide about the important physical chemical processes that are operating during planet formation that may shape the distribution of planets, and especially rocky planets that may or may not be like Earth. Okay, so let me start. So what you see here is just, of course, an illustration of the only planetary system that we knew until about 25 years ago, with the Sun, the 4 terrestrial planets, and the ice and gas giants in the outer solar system. Now, that has changed since then dramatically, and we, of course, do not see the solar system as the only way anymore how you can create a planetary system. But there are many other examples, especially the ones we found so far are rather unusual from the way that we would have interpreted or what we would have predicted 25 or 30 years ago. So it's really a revolution in our understanding. But what I want to do here is highlight especially the differences in composition that we've seen so far, and that are really beyond everything that we have anticipated. We anticipated before. So what you see here is the mass radius diagram of exoplanets that were known until 2017. So of course this data changed a bit, but not dramatically, in order to illustrate the point I want to make here. So on the x-axis, you see mass of a given planet, and on the y-axis, you see its radius in Earth radii. Dots are individual planets, and the color scales to the equilibrium temperature for a given planet. Now, what Earth is down here, where there's this arrow, and that basically means there are these different lines, isolines of composition. So that means if you're somewhere up here, then your planet is mostly composed of hydrogen and helium. So potentially like Jupiter or a gas giant planet. If you're somewhere down here, then your planet is more composed of dense material, potentially like iron, that brings that brings the suggestion up of supermercuries, for which we have actually we find more and more planets that have these densities. If you would be somewhere around here, that means that your planet could be potentially made up of mostly water. So there's an ongoing debate in the exoplanet and the planet formation community about the existence of these planets. So whether Ganymede-like objects, like we know from the moons in the outer solar system, if these things can actually exist in a planet-like orbit. But at least we know some celestial objects like Ganymede who have this, have very high water content. And so we will see, I guess, in the upcoming years if something like this can exist on, let's say, more temperate orbits, potentially Earth-like orbits, which is sometimes called the habitable zone. Now, the question for me and many other people becomes, of course, what is the right mixture? You know, what defines an Earth-like planet, and how do you form something like this? To illustrate my point, how difficult it is to actually make this distinction from the current data, I illustrate here on the bottom right the difference between an Earth-like world and a water world. So you see that if an Earth-like world, you know, like the Earth has about 0.18% of water, typically the question is, we ask the question, how did Earth get its water? But what if it were the other way around, actually? What if it were, you know, like water is abundant, and the question isn't how it gets the water, but how to get rid of it? The reason I say this is that if you mix a bit more of water into, if you would mix a bit more of water into the Earth, let's say 1%, which is not too much. Chondrites in outer solar system objects have about 5% of water, and Ganymede has even more, comets have more. So if you would only have 1% in the planet, then the water actually would exceed, this amount of water would exceed the storage capabilities of the terrestrial mantle, so the planetary mantle, and the water would actually be stored on top in a global ocean. That is way too much water, so there would be no land at all, but also actually the pressures at the bottom of this global ocean would be very high, meaning that the planet would actually not have a global ocean, but a global ice layer. And that would inhibit any cycling between of greenhouse gases between the atmosphere and the interior. And therefore, these types of planets wouldn't have any weathering or thermostat that would keep their surface temperature roughly constant over billions of year timescales. So actually, too much water is not so great, you know, and it can potentially be a limiting factor in being a real, like an Earth analog planet. Now, what I want to do now is I want to ask the question, which physical processes actually could be important for this? And for that, we need to go back to the formation phase, because during the formation phase, the volatiles are most easily exchanged, and volatiles are delivered, or planets can get rid of them. So where we start now is during the protoplanetary disk phase, when the planets are forming. So what you see here is an illustrative movie. I hope it actually renders, the movie renders over the internet. So what you should see is a protoplanetary disk around its central star, and then we zoom in to local regions where the disk is inhomogeneous. Actually, what is shown here is the process of the so-called streaming instability process, which is one of the current leading theories for how the earliest planetesimal families formed, which are basically the seeds of the planet, which then further coagulate and form planets, terrestrial planets, potentially giant planets. Now, the timing of this can be rather complicated, and we have only very limited and basic data about this from protoplanetary disks. Data becomes better and better, and we get a much better overview with this, with the Atacama Large Millimeter Array. But so far, the timeline and most of our understanding of how accretion actually works comes from the solar system still. And even if we get better and better data, we will never be at the point where we can have the chronological information that we have for the solar system, because we can only see snapshots for a given extrasolar planetary disk. But for the solar system, we have actual chronological data from geochemical dating methods. So this is shown on the left-hand side here. You see again an illustration on the top left, and then on the bit to the right, you see an actual disk from the Atacama Large Millimeter Array. On the left bottom, you see a chronological timeline, roughly relatively coarse so far. So the disk and the solar system lived for around 4 million years approximately. The earliest known solids on the left-hand side is there really actually? Yeah, okay. You don't see. Okay, I assume you don't see my mouse. That's a bit unfortunate, but that's we're gonna have to live with that. So no, you don't see it. Is there any way? Do you know this? Yeah, I don't know. Okay, well, I'll describe what we're seeing. Okay, so you see, after the formation of the CAIs, which are the oldest known solids, what we know in the solar system, roughly correspond with the onset of the accretion disk and the birth of the sun, followed by iron meteorite formation, which are really the oldest known objects that we know. So magmatic irons, which formed in the inner solar system, followed by chondrite accretion, which are the more pristine object, less thermally altered objects. And then we also have some chronological information about the accretion of Mars, which we will see on the next slide, on 2 slides from now, actually. So what I want to do now is actually I want to describe 2 complementary observations about planet formation that really started to take shape in the last few years only. The first is actual temporal fragmentation of the planet formation process. So we have chronological evidence not only anymore from the solar system, but also from exoplanetary system. Coarse, but there is some. So on the left-hand side, what you see is evidence from exoplanet systems, especially the y-axis shows you mass of solids and disks of exoplanets, and the x-axis stellar mass. Now the lines actually, class 1, class 0, 1, and 2, show the mass budget in dust grains, in millimeter-sized dust grains in exoplanetary disks from ALMA, and the dots are exoplanet systems, showing that class 2 disks, which are actually which is the long-lived phase, do not have enough mass in dust anymore to explain the observed exoplanetary population. This suggests that the onset of planet formation, actually, when dust gets transferred into larger objects, is really early during the infold stage, the class 1 or class 0 phase. Now, on the right-hand side, we have similar complementary evidence from the solar system. What you see is time after CAI, again, time after the onset of the solar system formation, in millions of years, and you see ages of magmatic iron meteorites. They represent the timing of iron core formation in the earliest planetesimal families, but this needs some heat-up phase, meaning that the planetesimals actually formed a bit earlier than that, which also suggests strongly that these families formed during the infold stage of the solar system. Now, in addition to this early onset of planet formation for the solar system, we have actual evidence for protracted accretion. Now, this comes from geochemical dating methods. On the left, you see this both for Earth and for Mars. On the bottom left, you see this yellow area shows basically the approximate accretion, the evolution of mass over time for Mars, and showing you that at about 2 to 3 million years, Mars accreted to about 50% of its mass. It took much longer, several million years potentially, until it was finally formed. The Earth took even longer. Of course, the moon forming impact was several tens of millions of years, potentially 100 million years after solar system formation, but it took definitely much longer than the accretion disk to finally to fully grow the Earth. Now, that is interesting because it kind of relates to our understanding of what the difference are between the systems. For instance, the formation of super-Earth on the top right. It has been suggested that the formation of super-Earth is caused by difference in pebble flux. So pebbles are coagulated dust grains in disks, suggesting basically that there's a fundamental difference between systems that are solar system-like, which have a low pebble flux in the inner solar system that would form terrestrial planets, and other systems that have a higher pebble flux and form then eventually super-Earth. At the bottom, there's the different alternative suggestion, basically, that actually the accretion of super-Earth just requires a higher solid density, but the systems that form super-Earth then accrete late during the disk phase, so that you do not accrete a lot of gas. Now, there's additional information actually to this temporal evidence. We have spatial evidence for spatial fragmentation of planet formation. On the left-hand side, you see evidence for substructure in the dust component of disks. And on the right-hand side, you see the similar complementary evidence from the solar system. So what you see is the clustering of meteorites, or the different planetary objects, which can either be, let's say, planets like Earth or Mars, but also meteorites, which cluster in different positions in isotope space. So what you see is chromium-54 versus titanium-50, and inner solar system objects cluster in one part of the diagram, and outer solar system, the carbonaceous reservoir, clusters in the outer part, suggesting that there was some sort of structuring happening in the solar system by some unknown or debated mechanism. Now, before I keep going, as many people or several people have suggested that this clustering, for instance, in the solar system, also the reason for these structures in disks are already formed planets, I will follow a different line here and argue instead that especially the clustering of the isotopic, this isotopic clustering in the solar system is rather inherited from the movement of the snow line in the early disk. So for that, let me explain here these few diagrams here related to the disk. So what you see is the disk from the side. The left part, which is full of water vapor, is inside the snow line, the water snow line. The right part is outside of the snow line. So at the snow line, when you go from the inside out, then the temperatures become low enough so that water can actually condense and be incorporated into ice-rich grains. That means that the solid density there is enhanced. It means that planet formation can act more efficient. Now, there are two effects actually that are relevant for planetesimal formation at the snow line. The first is the so-called traffic jam effect that is because grains actually interact with the gas and they feel a headwind. They drift inward very fast in the outer solar system when they coagulate on the outer planetary system. But then when they drift across the water ice line, the water actually sublimates, they become smaller, and their drift slows. That leads to an enhancement of the solid surface density directly at the location of the snow line, and therefore the solid density there is enhanced. This can trigger different mechanisms, for instance, the streaming instability, so planetesimals can preferentially form there. There's another mechanism that is relevant for the snow line, which is less often discussed at the moment, which is the cold finger effect. Originally envisioned to be the cause for the formation of Jupiter, the cold finger effect works instead of via dust grain drift, it works via the diffusion of water vapor from the inside out. So you have water vapor that is in the disk. The disk has some sort of some turbulence ongoing, or some mechanism of diffusion going on in the midplane, and some of that water vapor can diffuse outward and condense onto the grains just outside of the snow line, and then enhance again the solid density and lead to the formation of planetesimals. Now, these two mechanisms are different in their effectiveness and also their timescales. So the cold finger effect, the latter one, is fast but less effective, works roughly on a 1,000-year timescale, and the traffic jam effect is actually slower but more effective, works on about the 10 to the 5-year timescale. Now, what I'm going to do is work with my colleague Joanna Drążkowska from LMU Munich. She is an expert in protoplanet disk evolution and dust coagulation. And what we will do is we will try to explain the compositional and orbital evolution of the terrestrial planets from the extremely early stage. So for that, Joanna uses like an infall model, which assumes basically that the protoplanetary disk is built up during the infall stage. So basically, you have a homogeneous sphere that is shown on the left-hand side that collapses and builds the disk from the inside out. So the disk is built because of the material that falls onto the disk, and additionally, the disk viscously expands. Now, we will do this and look what this means for the build-up of planetesimals due to the streaming instability in such disks, and this is shown in a video here. So I'll play it first, and maybe I'll play it again and explain what's happening. So if you focus first on the bottom part of that movie, it shows the radius in AU on the x-axis and time in mega years on the y-axis. So what you've seen is basically the movement of the snow line is kind of irregular. First starts actually after about, in the beginning, there's no material there at all. So this first wiggle isn't really anything. But when this the snow line starts to move out as soon as the disk builds up really. Now, after a while, it starts to migrate inward again. There are two enhanced density regions. The color is the planetesimal formation rate, meaning the amount of planetesimals in surface in mass that is formed over time. What you see is there are two disconnected parts, two distinct bursts of planetesimals. The first one caused by the cold finger effect, which is fast but less effective. And the second one by the traffic jam effect, later and further out. Now at the top you see the surface density that is created by this. The inner part, less massive. It actually integrated is about 2 Earth masses. And the outer part, more effective, further out, and more mass on the order of a Jupiter mass. Now, what we're arguing here is that this sequential buildup of 2 planetesimal reservoirs in fact explains the or suggests an explanation for the isotopic dichotomy that we observe in meteorites at present day. Now, why should that be? So actually to begin with, the reason why astronomers were confused or surprised about the isotopic dichotomy about 10 years ago, or many people didn't really see that there's a meaning for this, is that actually dust drift in the solar system should act to homogenize a planetary system. So that's discovered in the 70s that dust grains drift very quickly on the order of 10,000 to 10,000 years. And that means because protoplanetary disks live several millions of years, this dust drift should lead to a very rapid homogenization of initial primordial isotopic heterogeneities in the disk. Now, we measure here what would happen in our disk model. So what we need is basically we need some sort of information dense content that is initially there, in homogeneity in the isotopes, that is not mixed completely after the disk is gone. So what we will consider here is a pebble that sits initially in the outer solar system and then streams inward toward the inner solar system. So the amount of admixing of outer solar system pebbles into the inner solar system can be seen as a measure of that isotopic mixing. So I will consider like one stage and measure the pebble flux at 2 AU, and I'll measure the pebble flux at 15 AU and see if that matches. If that matches, that means that all the material that was initially outward comes in and gets mixed into the inner solar system, meaning that the total integrated isotopic signal should be roughly should be of similar magnitude. Now this is what we observe in this the simulation. So on the right hand side, the colors match. So the red line corresponds to 2 AU and the blue line corresponds to 15 AU. X-axis shows time after CAIs, where we assume that in the disk model actually starts at CAI formation. The y-axis shows the pebble flux in Earth masses per million of years. So let's focus first on the blue line. The blue line first goes up. That is because the disk is built up, and then it goes down over time because of dust coagulation and drift. Now, the inner solar system initially behaves similarly, but then actually it goes the line goes down much quicker than the outer solar system. And this difference you see, which is called their DM reservoir 2 dt, is actually the buildup of the mass of planetesimals in the outer solar system. That means that material that is initially in the outer solar system does not actually make it into the inner solar system. And the difference there is more than 1 order of magnitude, up to 2 orders of magnitude at about 3 to 4 million years. This means that actually the isotopic signal that is present in the outer solar system does not make it into the inner system because the material gets incorporated into the planetary reservoir in the outer solar system. Okay, so that seems maybe reasonable. I don't know, maybe it has some meaning for the isotopic dichotomy, but there's a big issue. We form in this simulation all planetesimals, even reservoir 1, which should be representative of the terrestrial planets in the solar system, is extremely wet because it forms beyond the snow line. That is weird because Earth has, in comparison, for instance, to Titan or Europa, a much smaller water content, as I explained in the beginning. So what's the problem, or how can we solve that issue? The reason is, what is typically not considered in models of terrestrial and planet formation is the actual geophysical evolution of the building blocks itself that operate during the formation on the same time scales of the formation of the planets. Now, what you see on the left-hand side is the amount of radioactive heating that comes from the decay of radioactive isotopes in the early solar system. X-axis is time after solar system formation, millions of years, and y-axis in watts per kilogram of silicate material. The different lines show different radioactive isotopes. For instance, potassium and uranium, the vertical, the near horizontal lines are long-lived ones, which are still active on Earth today and power partly the tectonic evolution of Earth. But what you see is that in the early solar system, in the first few million years, aluminum-26 was really the main driver. It's a very short-lived radioisotope of 700,000 years. What it did is the energy that is injected into the planetesimals during that phase is so high that it could melt silicates and lead to other processes such as water degassing. That is shown, so we can make computational models of this, such as this one on the right-hand side. This is a 3-dimensional model that we did a few years ago. What you see is a planetesimal, like a cut into a planetesimal, and you see how the silicates in the planetesimals and the magma is deforming. So color scales with temperature, it's hot in the interior and cold on the outside where it's bounded by space. Now, here you see a quantitative parameter space of that with planetesimal radius and formation time. You see the temperatures that are reached in color. So for the largest planetesimals that are formed the earliest, meaning with the highest amount of aluminum-26, the temperatures were so high that the silicates really melted, and these things were miniature lava worlds that floated in space and coagulated further. Now, that has also severe implications for the compositional evolution, the structural evolution of these bodies. Let's focus first on the green lines now. The leftmost one, H1, corresponds to the right-hand side, also the H1 part where it has water ice melting, and H2 corresponds to H2 and similar with C1 and C2. So this has implications which we will care about here for water ice melting and for core formation. So let's start with water. If you have consider an initial comet-like composition, let's say 30 to 50% of water ice, then you will lose that because of this massive heating. So if you are somewhere on that H1 line, then your planetesimal reaches temperature where the interior of the planetesimal, the water ice, melts, reacts with the ambient rock. The liquid water during a specific amount of time actually moves along a down temperature gradient to the top, where it's actually more vulnerable, for instance, due to collisions with other bodies. If it's hotter, or so meaning earlier formed, or if the body is larger, then the entire planetesimal dehydrates, as seen in the H2 illustration, where basically the heating is so high that no stable hydrous phase can be contained anymore in the volume of the planetesimal. Core formation is important actually for understanding the chronology. I will show that in the next slide. So core formation means the separation of iron from a silicate mantle. So there are two different mechanisms: percolation, which acts a bit on during the lower temperatures, and rainout, which only works if the whole of the planetesimal is basically molten miniature lava planet. Now, So what we do here, we bring those two things together. The disk and dust dust coagulation simulation, planetesimal formation with our interior models of those planetesimals, and we ask the question if such a model can reproduce the clustering and the timing of meteorites that we observe from geochemical records. So this is what you see on the left-hand side. A shows so this plot on the top shows the ages of meteorites actually that display aqueous alteration, meaning the reaction of liquid water with some silicate material for the non-carbonaceous reservoir and the carbonaceous reservoir. So in this are our simulations. Basically, what we do is we take these formed planetesimals and process them, compute their compositional evolution of the entire planetesimal swarm for reservoir 1 and reservoir 2. What you see now is on the x-axis time after CEIs, and on the y-axis see the fraction of final planetesimal population, meaning the amount of material after the end of the simulation that has undergone a certain evolution. What you see is that the reservoir 1 actually shows a peak. That means there was a massive amount of hydrothermal activity in these planetesimals, but it goes down again. That means that temperatures reach temperatures that were too hot for any water to be retained, so no signal in these simulations could ever be recorded. Now we only have one age, which corresponds to the amount of material that is left over, but especially for reservoir 2, the peak that for hydrous activity that you see here coincides with the clustering of the ages for aqueous alteration in the carbonaceous reservoir. So we do the same calculation for core formation. You see the clustering of the ages in the non-carbonaceous reservoir on top and the carbonaceous reservoir as well on top. And here you see our simulations where those two red lines correspond to reservoir percolation and rainout core formation, which are the main main mechanism for core formation. The clustering of the ages is reproduced both for the carbonaceous and the non-carbonaceous reservoir in red, and the carbonaceous reservoir in blue, corresponding to our reservoir 1 and reservoir 2 respectively. Okay, so let me shortly summarize this. I have like maybe 5 to 10 more minutes. This was for the solar system. So let me shortly go very, very quickly through this. The main points here are that this model that we basically built together reproduces the meteority chronology in the inner and outer solar system. It suggests a very specific accretion process or chronology for the terrestrial planets that starts with collisions initially, which actually are more effective in the very early stage. Then there's a brief phase of pebble accretion, which is then again succeeded by collisions, because during the late stage, actually the inner solar system in our simulations is, without the presence of Jupiter, is deprived of pebbles because they are built up actually into planetesimals in the outer solar system. That leads then to compositional and isotopic reservoir separation. And the resulting dichotomy that we observe, both compositionally and isotopically, is a result of the spatially and temporally distinct buildup of planetesimal families in the outer, first in the inner and then in the outer solar system. In particular, the geophysical evolution is driven by the difference in radiogenic heating due to aluminum-26. This predicts a water accretion sequence that is actually quite different to what is typically suggested, namely first initially water-rich, but then depleted material that is succeeded by dry, and then potentially again a phase of water-rich material due to scattering from the growing giant planets eventually. Now, I started with the exoplanets, but now I talked for like, I don't know, 15, 20 minutes about the solar system. Now let's take that turn again. And so what is the point here? Why did I talk so much about the solar system? So the reason here, the main crucial ingredient for many of those things is the presence of aluminum-26. Now the point is actually that aluminum-26 may be highly unusual in the solar system relative to other systems. The reason for that is that aluminum-26 is synthesized and fused in massive stars during the Wolf-Rayet phase, or supernova actually, for stars above 20 solar masses. And it was not formed in situ in the solar system. So the presence of aluminum is due to an external source, actually. That means that the solar system during its early evolution must have been close or in the vicinity of a massive star that could inject that material. Why is that important? Because our standard picture of star formation involves that most of the stars actually form in clusters of stars. Now, on the left-hand side, you see a picture of such a star-forming region. On the right-hand side, you see a classical simulation of this event, which is probably outdated by now, but still illustrates my point, where stars in these star-forming regions form along filaments of collapsing clouds. The typical star-forming region is probably a few hundred to a few thousand stars. Roughly half of all stars in the galaxy are formed in intermediate to massive star-forming region. About half of the stars in the galaxy are formed in low-mass regions. Now, low-mass regions have a lower probability of having high-mass stars around. That means that stars or planetary systems that arise from high to intermediate to high star-forming regions have higher probabilities of having aluminum-26 in them. Now, we have done computer simulations, n-body simulations of that process, of one of those processes that are considered for the injection of aluminum-26 in the planetary systems, that is shown on the right. So in red, you see low-mass systems, which potentially are solar system analogs. And blue, you see massive stars, O-stars, which at some point go supernova and eject their freshly fused material into the surrounding, potentially enriching planetary systems in their surrounding with aluminum-26 or other short-lived radionuclides that can trigger these geophysical processes that I talked about. So here you see such a supernova remnant. Now imagine this thing going off in a star cluster, and this is a disk that is very close by. So you see the flow direction indicated. So then this disk will deform because of the ambient flow, but some of the material, especially the dust component, will be incorporated into the material and then incorporated to the planetesimal, where they can contribute to the heating. Now, the average statistics that for these specific simulations, there's an ongoing debate in the community, and it's not clear what is the actual fraction of systems with solar-like levels. So the answer we have provided here in that work using that mechanism, which is direct disk injection from supernova ejector, is roughly shown here on the left-hand side, the statistics. We would argue that about 5 to 40%, very strongly depending on the morphology and density of the star-forming region, have systems with solar-like aluminum-26 contents. X-axis shows the prospective radiogenic heating in extrasolar planetesimals, again, watts per kilogram of silicate material, and the y-axis, the fraction of planetary systems. Now you see where the solar system actually goes through this, but what you see here only are enriched systems at all. Most of the systems are actually at zero because they're too far away from a supernova in these simulations. Now, I told you in the beginning that planet formation acts quite early, so that means that if these things get incorporated into planetesimals, the heating will be intense. And we have done 2 years ago, actually by now, we've done computer simulations to simulate that process, what it means for the statistical compositional evolution of exoplanet populations potentially. Now, a diagram on the left-hand side that you already know. Now, this time, however, the y-axis scale to a solar system abundance, meaning that 1 is the solar system, then we go from a tenth of the solar system to 10 times the solar system. Color shows final planetesimal water abundances. These are roughly the sizes that we expect from the streaming instability in asteroid belt reconstructions. So when we now insert these populations into a planetesimal population synthesis code, where you make certain assumptions about how the growth of the planet happens during the disk phase, now assuming that you have an initial seed, that planet populations or planet formation is more effective beyond the snowline, and then following the entire growth from the initial seeding process, coagulation via planetesimal collisions, and then generating in computer simulations the diversity that is observed when we vary systematically the planetesimal radius and the aluminum-26 content in those systems. Now, the result of these simulations are shown on the right-hand side. So we're assuming that the typical planetesimal size in these systems is 50 kilometers in radius. The results you see are only for G-type stars, to simplify it for the presentation, and I only show the statistics for planets that end up being lower mass than 10 Earth masses, meaning super Earth at maximum. Now, what is shown is a histogram of final bulk planet water mass fraction at the end of the disk lifetime in weight percent. What you see is that planetary systems with low aluminum-26 content end up very water-rich, which is what I said in the beginning. That is because the planet formation process is more effective beyond the snow line. And when these planets acquire a substantial amount of mass during the disk phase, then they will migrate inward, which leads to very water-rich planets in the terrestrial planet formation zone as well. Now, if we increase that number to solar system-like or higher abundances, then these planets systematically dehydrate and reach levels comparable to the terrestrial planets of the solar system. Now, that has a substantial effect on the planet radius, as I told you in the beginning, because the density of that water layer, if you have several weight percent of water, is actually quite high. It's so high that it will potentially be measurable with upcoming exoplanet surveys. This is shown on the top left, statistics for these simulations. So focus on the blue line, actually. This shows protoplanets in our simulations with solar system-like aluminum-26 abundances. They are compared to simulations without any aluminum-26. The x-axis shows predicted mean transit radius deviation. So imagine we compare two populations of planets, one sourced from without any aluminum, the other one with lots of aluminum or solar-like abundances. The y-axis then shows planet mass. So if you find, let's say, a Mars mass planet at 0.1 Earth masses, then this planet is in systems with solar-like abundances. It is solar-like aluminum-26 abundances. It is about 10% smaller in transit than if it were from a different one in a statistical fashion. Meaning that if you would be able to compare statistics from those two populations, we would find a systematic mean transit radius shift. Okay, so this is the prediction for this, and the upcoming missions, such as, for instance, the European Plato mission, are currently promising that they will be sensitive to these radii shifts. So maybe we will be able to verify these predictions in upcoming years. And with that, I want to finish. I think my time is over. Let me very shortly summarize. So our work suggests that because of the difference in radionuclide content across planetary systems, there should be an observable difference in the compositional trends that we will see in planetary systems, where enriched systems with lots of aluminum-26, like the solar system, are able to form water-poor protoplanets or planets in the terrestrial planet formation region, whereas non-enriched systems actually lack this internal heating mechanisms and tend to form ocean worlds. That may be traced by the specific chronology and the compositional deviations in the inner and outer solar system. And what we really need, of course, is we need to connect this with future space missions and laboratory studies to both confirm these predictions and get more information from, let's say, asteroid belt objects, but also, of course, from exoplanet-focused missions that, for the time being, will focus on statistics. With that, I'm done. Thank you very much for your attention.
Hi, Tim. Very nice presentation. Very dense presentation. A lot of information.
Absolutely.
And with a certain complexity involved on it. I don't know if is there any question, but I don't know if I missed the point, but what's the dependence of having giant planets in the system? I mean, it does not depend on that. Your conclusions, those that you present here in this last slide, it depends mainly on the aluminum-26 amount you have in the system. But if the system has formed some giant planets or not, that is not going to affect these terrestrial worlds. I mean, in terms of amount of water.
It will, certainly. But like we argue that indeed the effects from the heating, from the coagulation process should be measurable on the terrestrial planets. I agree with you that there should definitely, I mean, I think that it's hard to argue against that there should be a difference between a system with a Jupiter or without a Jupiter. But I think I believe that there are some mechanisms that may have a similar role to play, which are typically neglected, and I argue that this is one of those mechanisms. So, for instance, in the specific model that I explained to kind of reconstruct the diverse, so the solar system itself, that was really tuned to explain the observations that we see in the solar system. In this model, the terrestrial planets actually accrete before the outer solar system, and that means that the influence of the outer solar system is there because it preserves the inner solar system from pebble flux later on, but actually the initial distribution of the solids is already there right from the start before the outer solar system population actually forms. And I think that is different from what is typically, let's see, considered in let's say starting conditions in dynamical simulations.
Okay, I got the point. So it somehow would not mainly depend on having or not what's in the outer solar system would not be, let's say, determinant for that.
For instance, what could happen, and for what is definitely it will be important, is if the snow line could, at later stages during the disk evolution, could still make it again inside the inner solar system. Now then, this has been suggested in the literature several times, I think, then this giant planet population would kind of shield the inner solar system from this, again, moving of the snow line to the inside. But yeah, indeed, there's an additional effect that we believe is making an imprint on the compositional evolution of the planets.
Yeah. Okay, good. Okay, let's see. Is there anybody would like to make a question or any comments on that, please?
Yeah, I saw that someone, Ricardo, mentioned how I could have shown my mouse, but it's too late now. Thank you for that.
Yeah, he said at the beginning, but I thought would
yeah, I couldn't see it. I didn't have the chat.
Yeah, but I thought would disturb your presentation. I left it go.
Yeah, too bad.
Okay. No, but I think it was fine. Your slides are very, very good. So it was okay. Okay. So you already commented. So in terms of Plato, what are your expectations about Plato, the mission?
I mean, it will take a while. So we hope, of course, that it will start as with like the anticipated. I think currently it's 2025 or 26. I'm not sure. Okay. So I mean, yeah. The issue is that our simulations here, for instance, even though for instance we took into account for the ones I explained for the exoplanet statistics, they take into account atmospheric loss, but obviously this process will be more effective, more seeable, let's say, in toward outer parts of the planetary systems, because these parts, let's say temperate orbits, are less affected by atmospheric loss. But Plato, of course, like every transit mission and every exoplanet mission, will see close in orbits first, meaning we will have to wait until the statistics actually build from the inside out, really. And so, yeah, I hope that Plato can achieve the sensitivity it promises at the moment. I mean, there are other exciting missions. For instance, the TESS mission at the moment is providing a much better statistics than I think everyone had hoped, had dreamed of. So maybe they can do like some good statistics before. Ariel is there, but it has a different focus, I guess. I think there are 2 questions in the chat, I believe. Did that answer your question?
Oh, okay. Yes. Thank you. So, Luana, would you like to make a question?
Yeah, sure. Hi, Tim. Nice presentation. Congratulations. You mentioned that you can determine the radius of the planet, of the exoplanet, by knowing the aluminum-26 of the system. I'm not sure I got it. How you can determine that?
So no, yes and no. I didn't. So that's really important point. So we're not saying that the radius of a specific planet is telling you anything actually about the aluminum-26 content of the system initially, but in a statistical fashion. So when you have many systems forming, and like a subset of those is heated from the beginning, and the planetesimal formation process, or the planet formation process of rocky planets, actually is dominated at least partly by rocky planetesimal accretion, meaning coagulation, then we argue that the subset, which has a lot of aluminum, will be substantially drier because it's dehydrated from the inside out. Whereas this other part, this other subset, which has no aluminum, accretes with much more ice or water-rich planetesimals. And therefore, if you compare them in a statistical diagram, in a mass radius diagram, for instance, then they should have an offset relative to each other, where the system without aluminum forms more water-rich planets, meaning they will be larger, will appear larger in mass radius space. So we will not, if you don't have two systems or just two exoplanets in different systems, you will never be able to say, okay, this is because this and this, but we argue that there should be a statistical observable effect. Yeah.
Oh, okay, I got it. Thank you.
Okay, good. And well, Heli Blanco actually wants an email contact. So if you could just.
Oh yeah, of course. I can, yeah, I mean, I can just write my email down here, or of course you can write me whenever. Of course, any happy. Also, I'm no professor, by far not. Yeah.
Okay.
Yeah, I don't know. Do you? I have a question for you actually. What do you think about this dynamically? I'm happy for any comments. They can be negative, you know.
Yeah. Well, the point is try to figure out. That was my question about the giant planets. So the question is, how would that affect the model? For instance, you know, we have all these models about the evolution of the solar system when you have that huge migration from Jupiter getting closer to the location of Mars and then going back, you know, the
grand tech, yeah.
Yeah, and so the point is, in terms of solar system, we have so many details being studied nowadays in terms of dynamics, orbital dynamics, evolution, and the models are, let's say, you have some ideas, but they're converging somehow to, you need some approach that have to be made to form, for instance, the limiting to form Mars, and for instance, to get the main belt with kind of mixing of components, ordinary chondrites and others. So we have in our field a lot of the dynamical details. So to me, it's impressive to get so much information as you got without, let's say, I'm not criticizing, I'm just saying not paying much attention about the model. So how sensible are your results to this kind of model? I do not have a let's say conditions to say now how sensible would be. So
yeah,
I think that's the point.
I agree with you. There's so like I can be specific in this respect, in the sense, so especially the small mass of Mars is only a problem if you assume that the initial planetesimal disk is homogeneous, right? So there have been models by now that argue like that, not only one, but like the motivation for the grand tech itself, for instance, was basically that terrestrial planet formation produces in a small mass if you actually start your accretion from a truncated disk, which was only very small, located around the terrestrial planet formation region. Now, the alternative actually of just truncating this disk afterwards is just primordially forming that disk already truncated by a planetesimal burst at the exact right location. And our model does not exactly reproduce this, but our model actually has some sort of, it produces like a distribution around the terrestrial planet formation region. Starts further out, this distribution is further out, but also the planets actually need to migrate during the disk phase if we start early. So I don't say we can solve that issue, certainly not. I just think that many of those issues eventually are more volatile than they may seem. So what I would really like to do is indeed what you actually say is what the next step for this especially for this very specific model for the solar system is take this initial distribution of planetesimals and then insert them into a dynamical model. The problem, however, I see is that we would need to have a combined model, because the planetesimals are forming while they should also already undergo dynamics, right? And I think no model so far is just computationally able to actually resolve planetesimal formation, dust coagulation, and orbital dynamics at the same time. Yeah, so I think we TBD, let's say.
Yeah, but I think that's the front end that perhaps we could collaborate.
Oh, I'm absolutely happy to do that. Seriously, yeah, I'm not. This is not my specialty, but I'm absolutely happy to talk about this. Yeah.
Yeah, the model you just talked about, the truncated disk, we published a paper on that. I think just proposing as an alternative, Isidoro et al. It's from our group. So
yeah.
Then we tried it. Yeah, the argument we used it was, well, let's think if as you said, if the disk is not uniformly distributed, the material will have some depletion at certain points, and there are some observations that show that there are disks that have some depletion. So you may have, and we have even studied, you do not need a truncation, a full truncation, but if you have 40% depletion at certain parts of the disk, you can reproduce the inner solar system. So we have showed that. But people didn't like, because we needed an ad hoc disk to produce it. So that was the people criticize in terms of this approach. But I still like that kind of idea, because there are a few examples that have this kind of depletion. So there's plenty of things. As I said, we in dynamics of solar system, there is a lot of things trying to be, let's say, tidied up. But in fact, you have more than one possibilities to produce the same effect, to reproduce what you find now. There are several discussions about that. Even the Grand TAC model is, let's say, it's not a matter of liking or not, but I don't think it's a good example of model, because it needs so much tiny tuning on the evolution that it makes it, let's say, more difficult to believe it should happen. So it's easier to have a disk with some fluctuations in the distribution of materials. It's more reliable. I think it's more, let's say, easy to accept than the other. But people keep trying on that. But so anyway, we could keep in touch and perhaps discuss on that later. Some collaboration on the simulations. Yeah, that's let's say, it's our field of expertise. So
absolutely, I'd be very happy to.
Yeah, good. So, do we have any other comments or question? Anybody else would like to make a comment or question? Okay. So thanks again. It was a nice presentation, and as it was a suggestion by Luana to invite you, and I like it because bring things that are complementary to what we do, and open possibility of new fields of research or collaborations and so on.
Yeah, that would be great. We should definitely talk about this once again in more detail, I guess.
Okay, good. So thank you very much.
Thank you, everyone, for your attention. Thank you, Luana, for suggesting. Thank you.
Okay,
Thank you for accepting the invite.
Okay. Now we move on to